Okay, so I just want to finish on the topic that we had to finish today, which is convolution. So yeah, so one small brief thing. So let me just disable my video for some time. Okay, so what I was saying is related to. I'm sorry. Okay, so coming to derived distribution, just a small clarification. So the last result that we saw, that fy of y, which is the vectors, these are vectors, is fx of h of y, okay, Jacobian of h with respect to y. Okay, so this is what we had done. Remember, this is sorry. This is not this, but determinant of. So let me just write this properly. This is determinant of the Jacobian matrix, which is basically the partial derivative matrix of H with respect to all the y variables. So this is what we saw, right? Now, the premise, the whole setup was as follows. What we had was x as a function of y, okay? Or in the same way, I mean, since this matrix's inverse also should exist, so we can also have y as a function of x as well. Okay, so these are the two ways this can be written. So sometimes, and depending on the textbook, you will see different versions of this. Okay, so what you will see sometimes is this will be fy of y, this will be fx of h of y. Okay, instead of the determinant, you will have 1 over determinant of Jacobian of not h but g with respect to x. So some textbooks give this way. Okay, the reason is this determinant of Jacobian of h with respect to y is 1 over determinant of Jacobian of g with x. Okay, these are having this relation. So if you write like this is one and the same thing. So Sheldon Ross book has this kind of a result in the book. Okay, so don't get confused when you see something like this. All right. So now let's come to the central topic, which is convolution. So if you remember, what we were interested is sums of independent random variables. So this is what we were studying. So we took an example, we took a case where z is equal to x plus y. Let us say x is distributed as so x density is fx of x, okay, and y's density is gy of y. So here x and y are single variables. Okay, so we were talking about multivariate. Now we are back to single variable. So this is like that. So now we want to find out basically the distribution of z. So this was the question. So what I said to you is that we will begin by finding out the cumulative distribution function, which is fz of z, which is probability that x plus y is less than z. Okay, so this will be the double integral in this region. Wherever x plus y is less than z, you will integrate the joint density. Okay. So now, continuing from this, so what we do is we let x vary freely. Okay, so you can let x vary freely, or if you want, you can even let y vary freely. Okay, but we will choose x to vary freely. So we will say let x take any value in the range, but y is upper bounded by z minus x. Okay, so then you have f of x y, x comma y dx. So first the inner integral is with respect to y and then x. So this is what we will do. Okay, so why this is correct? Because x is allowed to take any values like this, but y is upper bounded by z minus x. So x plus y will be a value which is x plus z minus x, which is z. So it will be upper bounded by a value z. So this is the right area. So this is what is the area that we were interested in, and it is actually giving that. So let's do some more simplification. What you get is minus infinity to infinity. So this fxy, since it is independent, remember this is sum of independent random variables. We can write this as fx of x into gy of y dy dx. Okay, so this we can pull out. We can pull out because it does for integration of y it doesn't matter. So we can write this as minus infinity to infinity fx of x. Okay, and this will be minus infinity to z minus x of gy of y dy dx. I hope everybody is following whatever I'm saying so far. Now, this is what we have been trying to do is fz of z, okay, is given by minus infinity to infinity fx of x, and this one is the CDF of g. So this will be gy of z minus x dx. So this I can integrate and I can get this. Okay. So that is good. So this is the formula that we should be doing. But now we can do some more simplification. Okay. What we can do is now take the derivative on both sides with respect to z. So you will get fz of z here. Okay. So I'm going to interchange the integration and this. So I'm pushing the derivative inside the integration. Okay. So this is I have talked about this before. This is the change of limits. Okay. So derivative is a limiting operation. Integration that you see is also a limiting operation. So interchanging is not usually easy, but let's assume this is all right. Okay. When you learn higher mathematics, you'll understand more of this. But for now, let us assume this is okay to do. So you will get fx of x. Since there is no derivative, no z here, it directly passes. So it comes over here, which has a z. So we have to take derivative of that, and now we will do chain rule. So this will give us gy of z minus x dx. Okay, so this is the convolution formula. Okay, so this is the convolution formula. So let's look at an example to make this more clear. So this is the formula. So if you have to find the density, you have to use this formula. Okay. So let us take z, which is equal to x plus y, where x and y are independent, okay, and identically distributed, okay, random variables. Okay, so these are called IID random variables. Okay, and x is uniform 0 to 1 and y is uniform 0 to 1. Okay, so this is what we will do. So now we have to learn how to do this convolution business. Okay, so that is the next order of the thing. So let's recall fz of z, okay, is going to be minus infinity to infinity fx of x into g of z minus x dx. So this is the convolution formula. Okay, gy. So now, so basically, whenever you have to convolve, you have to be a little careful. So let us draw this function. Okay. So what is g of, so if I draw gy, okay, so it's a value which is gy of let's say as a function of x. Okay, it's a value which is 0 to 1, right? It's a uniform. So what about gy of minus y, minus x? So let me just clear this. So gy of minus x, okay. So whenever x is minus 1, okay, when x is minus 1, minus x will be 1. So gy of minus x will be 1. So basically it flips. So whenever you have gy of minus x, you will have this kind of a situation. it flips. Okay, so this is point number 2. Now if I do something like gy of z minus x, so how does that do, how does that change? So basically what happens is you will have the same thing, but it will be shifted to z, whatever that value of z is. Okay, I have written it as though z is negative, but it could very well be positive as well. So as a function of x, this is how it will look. Okay, so this will be z minus 1. So in general, if you want to generalize this, okay, so if you have some gy of x, which is something like this, some shape like this. Okay, this is supported between c and d. So gy of minus x will be the mirror image. Okay, so this will be minus d minus c. Okay, and gy of, you can just plug in values and see. Okay, so this will be z minus c. This will also be same thing, but here it will be z minus c and z minus d. So this is something that you should learn in convolution. So what is the first thing? It is the mirror image and then shifting by the appropriate value of z. So why all these things are coming here? Because fz of z depends upon what is the value of z that we are talking about. Okay, so let's try to picture this. So if z is a, so first case is z is less than 0. Okay, so now fx of x, what it will be? Fx of x will be a value between 0 and 1. Okay. And gy of z minus x, it will be somewhere here. Okay, so this will be z, and this is z minus 1. So if you see, when you are trying to evaluate this integral, what do you note? There is no overlap. So when you multiply and try to integrate, the multiplication will be 0 throughout. So basically fz of z will be equal to 0 when z is less than 0. So this is 1. So now let's do the next region where there is an overlap. So let me choose a different color. So let's pick a value. Z is greater than 0, but z is less than 1. So what we are talking about is this region. Okay, so now there is an overlap. So let's draw that. So fx of x as a function of x will be this 0 and 1. So there is an overlap now. Okay, so there is like this, but z is smaller than or equal to 1. So it doesn't fully cross. So this is gy of z minus x. Okay, so this is the thing. So if I have to take the common area, what is the common area? You are going. This is going to be the common area. Okay, and both product will give you 1. So what we will get is fz of z will be an integral. The lower limit is from 0. The upper limit is z. Okay, and the common thing that I'm integrating is x. So this. Okay, so fz of z will be equal to z. I hope this is clear. So this was, so region number 1 was there is no overlap. Region number 2 is there is a minor overlap. Now finally region number 3, if you can be clever enough, you can visualize that. So fx of x will still be 0, 1. Okay, and region number 3 is z is greater than 1 but less than 2. So it's something like this. This is 1, this is z minus 1, this is z, and somewhere here there is 2. So this is gy of z minus x. Okay, so now fz of z, what is it? So now we have to look at the common area. This is the common area. This is the common area. Okay, so the when you take the integration, this will go to zero. This is a common area. So this part and this part is zero. This part and this part is zero. Okay, so now if you try to take the integration, it will be lower limit will be z minus one, upper limit will be one, and the integrand will be one dx. Okay, so this when I take integrate, if I try to integrate, I will get one minus z minus 1, which is 2 minus z. So this is for what region? This is for z, which is bigger than 1 but less than or equal to 2. So these are all the regions that is there. And finally, when z is greater than 2, the fz of greater than 2, fz of z will be 0. There is no overlap. So to summarize, fz of z is equal to 0 when z is less than 0 or z is greater than 2. Okay, so it will be z when you are between 0 and 1, and it is 2 minus z when you are between 1 and 2. Okay, so if you try to sketch it out, what you will see is that it looks something like this. So this is 2. So this is fz of z. Okay, so this gives the density that we were after. Okay, so what it is showing is that this region around the center is more common than this. See, that is easy to understand, right? So in order to get a value close to 0, it is necessary that both x and y are close to 0. So that is something new. So it's difficult to do. So that is why this comes. All right. So now, yeah. So if you do z is equal to x plus y plus z. So if you take, let's say, sum of three uniform random variables x plus y plus z. Okay, so if you do the same procedure, you will find that the distribution actually looks like a bell curve. Okay, so this will be 0 to 1, it will be having this trend. This 2 to 3, it will have this trend. Okay, so this looks exactly like bell curve. I will give you this as an assignment to do. Okay. So it follows the same idea. So let us recap how you do this. So first thing is you have to do the mirror image. So this is step number 1. Okay. Step number 2 is you shift that by a value z. This is step number 2. Okay. Then what you need to do is you need to take the second integration, that convolution, and then you have to overlap with the first. And based on that, you will get an area, and you have to integrate it and get the value. Okay. So that is the whole steps for this. I hope this is something that you can do on your own. All right. So this is about the thing that I wanted to tell today. Okay. So that's about it. I don't want to extend more. Thank you very much.